Hello everyone, and welcome to this video on vector calculus operators, the grad, curl and div in differential geometry on curved manifolds. So in Euclidean space, R3, vector calculus operators gradient, curl and divergence are defined using partial derivatives. However, on a curved Riemannian or semi-Riemannian manifold, these operators require the use of differential forms, the metric tensor and the Levi-Civita connection. This formulation generalizes vector calculus to arbitrary curved spaces, including applications in general relativity and differential geometry. So let's make a start. All right, so I might just remove that. Okay, so just a bit of background first. Let's just start Riemannian and semi-Riemannian manifolds. So let the pair Mg be an n-dimensional Riemannian or semi-Riemannian manifold with metric tensor G mu nu. And the Levi-Civita connection, nabla symbol, is the natural derivative operator compatible with G, so ensuring that the del G, nabla G equals 0, or metric compatibility. And this means the inner product of tangent vectors is preserved under parallel transport. Okay. So the Levi-Civita connection is torsion-free. So the torsion of the vectors xy is this object here for all vector fields xy. Now, this ensures the connection is symmetric in the sense that it does not introduce an intrinsic twist in the transported vectors. So when we use the Christoffel symbols of the second kind, the two indices below can be interchanged and they're both equal to each other. All right, that's it. Next bit. So we'll define the grad, curl and divergence using differential forms and the Hodge star operator. Now the gradient of a function. So in standard Euclidean space R3, the gradient of a scalar function where the function f belongs to the class of space of continuous functions on R3 is given by grad f is del f nabla f partial x times and then expanded in the basis partial over partial x. Okay, so it's a vector and this is the form it takes using the operator form from differential geometry. Applying the flat operator flat, we get the flat of this. We produce the same object, just instead of the basis tangent vectors, we get the basis covectors or the basis 1 forms dx, dy, dz. But this is just the exterior derivative of f. So df is just this, which is just the gradient vector flatted under the flatting operator. All right. Now, so we have df is the flat of the gradient vector, or the gradient vector is the sharp, that's the raising operator of df. So on a curved manifold, the gradient is naturally defined using the musical isomorphisms flat and sharp. So the definition, so gradient on a manifold now, this is general now, not just Euclidean space, but this generalizes it to curved space. So given a smooth function f, that's a map from manifold M to the reals, the gradient is the vector field grad f obtained by raising the index of the differential exterior derivative df. Okay, so grad f is the df with a sharp operator acting on it. All right. Local coordinate expression. So in local coordinates on the manifold x mu, so you have a local coordinate system, a local chart. Then the differential of f is df is partial f on partial x mu dx mu. Okay, with mu running up to the number of coordinates you have on that manifold. So using the inverse metric tensor G contravariant mu nu, we apply the sharp operator, sharp. The grad f is df sharp, is the sharp of this, and that can be expressed in component form as the inverse metric tensor multiplied by partial f on partial x nu, expanded in the basis tangent vectors, tangent basis vectors partial over partial x mu. So applying the inverse metric G mu nu to a covector 1 form, results in a corresponding vector because the metric defines the natural isomorphism between the tangent space and the cotangent space. This process is called raising an index, or the musical isomorphism, using the sharp and flat notation. Okay, so here's what's happening. So the components of df are partial f on partial x nu, and nu is expanding for however many coordinates you have. And the metric tensor g mu nu transforms these covariant components, partial f on partial x nu, into contravariant components. And the resulting object has the form of a vector in the tangent space because you're expressing it in the tangent basis vectors, using the tangent basis vectors partial and partial x mu. All right. Now I've covered all these sharp and flat operations in a previous video more than once, so have a look there. All right, so why this works, the metric g mu nu allows us to lower an index. So given a vector with contravariant components v mu, vector components v mu, we obtain a one form via the metric which lowers that index to give us the covariant component. For the inverse metric, g upper mu nu does the opposite operation. Given a one form covector v mu, we obtain a vector v mu equals g mu nu times the covariant components v lower mu. Now this is exactly what happens when we transform df into a vector field. Okay. So I'm just trying to show how the metric components raise and lower indices and how that applies to the sharp and flat operators. So hence the gradient in curve space depends on the inverse metric g mu nu, making it different from the Euclidean case. So in the Euclidean case, grad f takes this form. The grad f is a vector that takes this form, expanded in the tangent basis, partial f on partial x mu. But in curved space, we have the contravariant components, the inverse metric here, partial f, partial x nu, and expanded in the tangent basis. Okay, so divergence of a vector field. So to understand the divergence of a vector field, let's return to Euclidean space R3 and remind ourselves of a couple of useful tools. These include the Hodge star operator star and the flat operator B. So the Hodge star in 3D, three-dimensional space, R3, Euclidean space. So the Hodge star of 1 is then dx wedge dy wedge dz, Cartesian coordinates x, y, z. And the Hodge star of that is then 1. All right, so go back and forth. So the Hodge star of dx is dy wedge dz. The Hodge star of dy is dz wedge dx. And I've gone through all this in a video there's 2 videos on the Hodge star in this series, so have a look at those. I'm just reminding you of those results. Here they are. Okay, so the Hodge star of dx wedge dy is just dz. Okay, so let's take our vector x, apply the flat operator. Yeah, vector x can be expressed in terms of its components and tangent basis vectors, xi, contravariant, partial xi. All right, and then the flat operator acts on that, okay, and that we then employ the metric tensor to lower our components. Because when that metric tensor there acts on xi, it lowers the components, we get x lower I, and then expand it in the basis 1 forms of the cotangent space. So in R3, the divergence of a vector field x is this object here. All right, simply becomes div x is this. All right. Now, let's make use of the composed map. So Hodge star composed of the flat operator acting on the vector x is the Hodge star of the flatting of that vector, of the flat operator acting on the vector x, which we've just seen on the previous page. So it's the Hodge star of all this. And the flat of the vector here is this object here, this 1 form. Hodge star out front, well, we've seen from the previous slide the Hodge star of dx is dy wedge dz. The Hodge star of dy is dz wedge dx. And then the Hodge star of dz is dx wedge dy. The components here are untouched. I'll talk about that shortly. Okay, I've covered all this in the operator on the video on the flat and sharp operators. Next, so we need the exterior derivative d. So the exterior derivative acts on this. It may not make sense why I'm doing this at the moment, but you'll see what the end result is, and then you'll see why it makes sense. Okay, because what we want to do in this video is to find the grad vector, the divergence, and the curl of a vector. We want to see what form do they take using in differential geometry notation. What operations do we apply? Anyway, so let's apply the exterior derivative to all this, the exterior derivative to all that. So here we go, to all that. So we get dp, wedge dy, wedge dz, plus dq, wedge dz, wedge dx, plus dr, wedge dx, wedge dy. When we do that, so that's the partial derivative, that's the partial of p over partial x dx. Okay, wedge with all that and so on. When we do that, we can collect terms here. Now, I've jumped a step here because we're going to express in terms of dx, wedge dy, wedge dz down here. We're going to pull out these partial p over partial x and so on. But see, if you notice here, we have dy, wedge dz, and we have dx over here. Now, that's two steps. To move dx here, move one step, minus sign, move one more, another minus. That's two steps. And so what we get is an even number of moves. So that we can now move that, and that gets plus partial q on partial y. And then over here, dz, wedge dx, wedge dy, well, we can move the dz again two places. That's two moves. And so that remains positive as well because it's an even number of moves. So then we have partial r over partial z. So here we go. So the exterior derivative acting on the Hodge star composed with a flat operator acting on the vector x, okay, gives us this object here. Next step. All right, next we apply the Hodge star again to both sides. And when we do that, we take the Hodge star of this. As I pointed out 2 slides ago, the Hodge star of dx, wedge dy, wedge dz will just be 1. And so what we end up with is this object here. And what is that object? Well, it's the divergence of the vector x. But so this object here is just this, which is just the divergence of the vector x. Okay, so our next result is divergence of x is in differential geometry using the notation of the Hodge star and the differential and the musical isomorphisms is Hodge star d acting on the map Hodge star composed of the flat operator acting on x. So the local coordinate expression on a curved manifold will be this in local coordinates. So divergence is just this object here. I'll just talk about where that comes from in a moment. Just an object there, where g is the determinant of the metric. Okay. All right, so here's our rule again. The divergence of x is just these components here. In if I just go back a bit, in Euclidean space, in Cartesian coordinates, the metric we use there is the Euclidean metric, which is the identity matrix, and the determinant of that is just 1. So this becomes 1 over 1, so it does not need to explicitly appear. This becomes 1, and we just have the partial of x mu over partial x mu. Right? But on a curved manifold, we need to include the square root of the absolute value of the determinant. Okay, that's what comes there, and I'm hoping to generate an argument for that shortly. But, so this formula accounts for the curvature of the manifold through the volume element, the square root of the absolute value of the determinant of the metric, which replaces the constant Euclidean volume element, which was, if you remember, the constant Euclidean volume element was just 1, which is what I was talking about a moment ago. So these is 1 over 1, 1 here, and all that drops out. Now, I have a video showing how this result is derived, so I'm not going to go through it again here. It is titled Relating the Connection and the Metric, and there's a couple other results in there as well for you to look at. I'm not going to repeat them here because it'll just increase the length of the video unnecessarily because they're available in this other video. So please have a look at Relating the Connection and the Metric. All right, let's have a look at the curl of a vector field. Now, I did cover the curl briefly in this video mentioned here, but I'm not happy with it. And I want to do it from the point of view of differential geometry and not just quote some components and no argument whatsoever. Okay, so the curl of our vector. So in R3, let's go back to R3 again, and Cartesian coordinates, x, y, z. So the curl of a vector field x is given by curl x is nabla cross x or del cross x. And the curl of x becomes this expression here. Don't think I need to do that. You can do all that using your you can use the determinant and your cross product method and so on. But this is the result you'll end up with for our vector, which was x equals p partial on partial x plus q partial on partial y plus q plus r on times partial on partial z, okay? And then when you find the curl of that, which is this cross this, you end up with this object here. Okay, it's the stuff of vector calculus courses. But on a general manifold, we define curl using differential forms, or can define it using differential forms. So the exterior derivative of the flat of the vector x, well, is the exterior derivative of, here's our vector x, and we're going to flat that, so that gives us this object here. Now take the exterior derivative of that, which is d acting on this. Now p may be a function of the coordinates x, y, and z, so we must put all in there. Wedge that with dx. Then q here, the exterior derivative of all that, wedged with dy. Remember d acting on the q there, because again, q may be a function of x, y, and z, so we do need to do each one of those in turn. Same with r, so we write that out like that, wedge dz. Okay, now next thing to notice is that dz, wedge dz on the end, well, that's going to drop out, that'll be 0. Dy, wedge dy, well, that'll drop out, that'll be 0, and dx, wedge dx, well, that's 0 as well, by definition. So we don't have to worry about those. So we're then left with partial p on partial y, this one here, dy, wedge dx, plus partial p on partial z, dz, wedge dx. Okay, they're non-zero at the moment. Same thing over here, we need to take this first one and third one. And lastly here, we need to take the first and the second. So here they are written down there. Next stage then is we can collect things together. So for instance, dy wedge dx, or actually what I'll do is I'll do dy wedge dz, that's the order I did it in. So we'll have partial r on partial y, dy wedge dz. And over here we have, this one is dz wedge dy. But if we flip that order, then, because remember the wedge product is anti-symmetric, we then get minus partial q, partial z, dy, wedge, dz. So partial q, partial z over partial z. And we get a minus there. Then we can put those two together. Same thing here, partial p, partial z, dz, wedge, dx. Fine, that's plus. Where's the other dz? And here's the other one, dy, wedge, dz. Now, if we reverse that order, then we have to put a minus sign because of the anti-symmetry, and we get partial minus partial r and partial y, so we put that down there. So we get partial p on partial z minus partial r on partial x dz wedge dx. And then similarly for the last term as well. Okay, and this is looking a little bit like the curl. Still got a step to go yet. All right, now we apply the Hodge-Star operator to both sides. Hodge-Star to both sides here. And we know that when the, as I pointed out a couple of slides earlier, 3 or 4 slides ago, that the Hodge-Star of dy wedge dz will just be dx. The Hodge-Star of dz wedge dx will be dy, and the Hodge-Star of dx wedge dy will be dz. And this, wow, look at that. That looks like the curl, doesn't it? The curl of the vector x. Okay, then almost, because it's not a vector yet, is it? Because it's still a one form. So then apply the sharp operator to both sides. Sharp operator. When we do that, we take it from this one form to a vector. All right. We don't have to do anything with the components. Remember, we're still in Cartesian space here. And the metric that applies here is the identity matrix. All right, or the metric has to form the identity matrix with just ones down the diagonal. So nothing changes here. The components here don't change when we raise or lower indices. So the contravariant form of the index of the component is the same as the covariant form of the component. All right. So there's our curl x. So now what we've shown is that curl x is the sharp of the Hodge-Star of D acting on the flattered vector x. All right, and we'll say that this applies in curved manifolds as well, but it'll look a little bit different explicitly when we talk about the components. All right, so curl x is this in Cartesian space, in Euclidean space using Cartesian coordinates. Now let's do a little bit of relabeling because we want to apply this now to a curved manifold. Okay, so relabeling with V is this. Okay, we'll just stick to 3 dimensions because that's really what the curl is defined in. So the curl of this, right, as we've seen in Euclidean space in using Cartesian coordinates x, y, z. X is x1, y is x2, z is x3. Okay, now note in the Euclidean orthonormal system, the contravariant components are identical to the covariant components because the Euclidean metric is this one, and this doesn't raise or lower indices. It has no explicit change on them. We just multiply them by 1, which doesn't change anything. So we can, okay, so we're happy with that because remember how we use the metric in curve spaces to raise and lower indices on coordinates. So we can take a contravariant component, multiply it by the relevant metric tensor component, and we'll lower its index so it becomes a covariant component, from a contravariant component to a covariant component. I believe I showed that earlier on. So we can now express the components of the curl of V in R3 using the Levi-Civita symbol, epsilon ijk. So, and we'll do that because you'll see one short. So curl V, the components, the ith component of the curl of the vector V is epsilon ijk, and it's equal to this object here, okay? Because these contravariant components are identical to the covariant ones in Euclidean space. And so if we take here, for instance, I is 1, then j and k can be 2 and 3, or they can be 3 and 2. Remember, positive permutation, 1, 2, 3, makes this whole Levi-Civita symbol equal to 1. And an odd permutation, such as 1, 3, 2, because 2 and 3 have been swapped. Remember, j was 2, k was 3, and then if we swap them, that gives us an odd permutation, and so that gives us this whole symbol becomes -1. And so what we get here is partial vk on partial xj minus partial vj on partial vk. All right, and if I put 1, 2, 3, then that becomes I is 1, j is 2, k is 3. If you have a look up here, all right, j is 2, k is 3. Bearing in mind this, of course. Okay, minus that. So there's two possibilities you can have. There's two permutations. You can go 1, 2, 3 or 1, 3, 2. And hence we can write like this. But we can summarize it even further. We don't need to write both out like that. We can just use the Levi-Civita symbol and just write partial vk on partial xj. All right. And we know that once I is 1, there's only two possibilities for j and k. It could be 2, then 3, or it could be 3, then 2. One of those is positive permutation, one's negative. And so you'll get two terms. So we don't really need to write out this two-term expression here. We can just write it like this. Okay, that's in Cartesian space, Euclidean space using Cartesian coordinates. All right, so let's have a look at, though, on a curved manifold, how that's going to change. So definition of curl on a manifold, and when we say manifold, just mean anything, curved, not curved, okay? So for a vector field x, its associated one form is x b flat. All right, the curl is defined as, and we have a vector x, and then we can flat it using the flat operator. Okay, so curl x was the flat of all of this, the Hodge star acting on the exterior derivative of the flatted vector x. Okay, this involves taking the exterior derivative, dxb, which gives a 2 form, applying the Hodge star, mapping the 2 form to an n-2 form, because we're in 3D, don't forget. And raising the, hence the 2, raising the index using the sharp operator to obtain a vector field. So in general, curl only makes sense in three-dimensional Riemannian manifolds. In higher dimensions, the exterior derivative d naturally generalizes to produce differential forms instead of a traditional vector-valued curl. All right, so let's find the curl of the vector field x equals x mu partial over partial x mu. Just bear in mind we're restricting ourselves to 3D. So the curl of x will be the sharp of all that. So step 1, let's apply the flat operator. So inside the inner parentheses here, we'll take the vector x and apply the flat operator to it. So the associated one form of the vector x is the flat of x, is the flat of that. which in components then we use the metric to lower the index times the vector component x contravariant mu dx, and see how the tangent basis vectors become the cotangent basis 1 forms. Okay, step 2, compute the exterior derivative of our associated 1 form. So the exterior derivative of the 1 form xb or x flat is this, that. Okay, so exterior derivative of the 1 form, our 1 form is this object here, sorry. The exterior derivative is then, here it is, d acting on x flat. Okay, is d acting on that, which is now partial over partial x of lambda acting on this, partial x lambda, wedge dx lambda, just as before. Remember when we had p, q, and r in these spaces here, and then we took the partial derivative of them? Well, we did the exact same thing. It hasn't changed. We just have here, these are our components. Here's our vector components, x mu, and then we have the metric here to lower them, because that's what the flatting operator does. It lowers the components, the contravariant components to covariant components, and it raises the tangent basis vectors to 1 forms. Okay, so this object here is just exterior derivative acting on that. Is this partial derivative here, partial over partial of x lambda acting on this times dx lambda, wedge dx nu. The dx nu is already there. Okay, so that's our second step. All right, now we apply the Hodge-Star operator. So the Hodge-Star of a 2 form, dx lambda wedge dx nu in an n-dimensional manifold is given by, I'm just giving the general formula here, but we really only need here n equals 3. But I'm just going to give the general formula. So here we go. This, if we were in some other n-dimensional space, and this would be the formula you use. Okay, but here n is 3, so that'll be 1 over 1 factorial, which is just 1, so that'll drop, it won't explicitly appear. And we have here 1 over the square root of the absolute value of the determinant of the metric. All right. And then applying this to dxb, we get for n equals 3, dxb is the Hodge-Star of all of this. Well, the Hodge-Star of this is going to be a 1 form here. Okay, so the Hodge-Star of this 2 form in 3-dimensional space will become a 1 form. So we get a 1 form here, so we expand that. And we get the Levi-Civita symbol with all the indices lowered, okay, and multiplied by all of this. Okay. Now, as we remember how we've taken, okay, so we've gone from here, acting on this, and it gives us this object here. Okay, you can see how everything's still there. Now, and we still have the partial derivative of all this there. Now, step 4 is to convert back to a vector field. So to obtain the vector representation, because at the moment all we have here is a 1 form, to obtain the vector representation of curl, we apply the sharp operator, sharp, which raises the index. So let's have a look at that. Okay, so curl x is the sharp of all of this, which was on the previous slide. And so we get this, with the sharp operator out front. And what we're going to need to do is take this from the cotangent basis 1 forms to the tangent basis vectors. And we also have to raise, on all of this, we have to raise the index. So we get this extra g rho sigma here, which wasn't on the previous slide, and that comes because the flat operator is being applied, so we raise it. Okay, so we've got this. This factor can be pulled out here. We have, and what these 3 metric components here do is they raise each of the indices here on the Levi-Civita symbol and put them upstairs. So you can see rho sigma sigma, okay, that sums out the sigma upper and lower, and this becomes an upper rho. This lambda alpha, the alpha sums out this alpha here, upper alpha, lower alpha, they sum, the Einstein summation convention, and we're left with an upper lambda, and the same with nu here. Okay, beta, sum out, and we're left with nu. Okay, so we get we get Levi-Civita symbol, rho lambda nu times the partial derivative of all that, and then expressed in terms of the tangent basis vectors. So this object here is now a vector. The whole thing is a vector. Curl x gives us a vector in 3D. Here's our vector. Now this vector has components. Curl x rho is all of this. All right, they're just the components. Remove the tangent basis vectors there. We just want the component part. Okay, now we can go one step further because we can tidy this up and make it look a little bit nicer. So notice that the vector component x, the contravariant components x mu, well, we can use the metric to lower that component to the covariant case. So we get this covariant component instead because we've used the metric tensor to lower the components on the contravariant component here, lower the index. So the curl x rho, the rho component, is 1 on the square root of absolute value g, Levi-Civita symbol times, look at that, partial x nu over partial x lambda. Okay, that's what happens there. Next step, so local coordinate expression on our manifold, local coordinate system, coordinate chart in 3D curved space. The components of the curl are this, gives us that, where epsilon rho lambda nu is the Levi-Civita symbol. So on a curved manifold, we have the following results. Gradient vector is just the sharp operator acting on the exterior derivative of f, df. So now in component form, grad f is just, this is just in component form, but this is the whole vector because it's expanded in terms of the tangent basis vectors. If you just want the components, and it's these first two elements here, g mu nu, the inverse metric, times the partial derivative of f with respect to each of the coordinates. All right, but the whole vector is this. Div x is a scalar, that's this object here, and that can be written in local coordinates in this component form here. This is just a scalar. And then the curl, which produces another vector, is this object here, and the components of that are curl x mu is 1 on, as we saw earlier, the partial derivative of the covariant components over partial x nu. All right. Now you can always get rid of that covariant component if you don't want it, and simply use the inverse metric to raise rho again. All right, and then it'll be the partial derivative of all of that. All right, now, what you could do is replace x rho by writing g mu nu, the metric tensor, not the inverse metric, but the metric tensor times the contravariant component. My apologies there. Then the partial derivative acting on all of that. My apologies there. All right, next one. All right, so example is a gradient in spherical coordinates on a 2-sphere S2 with metric this. All right, the metric tensor is this, and the inverse metric is this. Okay, the determinant then, as you can see by of the metric tensor here, is just multiplying the diagonals together. You get sine squared theta. So for some arbitrary function that's a function of theta and phi, or one or two of those, or both, the gradient is just this. The gradient vector is just this object here, which you've expanded out. You get this. Okay, expanding that out in terms of the coordinates, theta and phi. Okay, you get partial f on partial theta times partial on partial theta in the theta direction, that basis vector there, all of this times this basis vector here in the phi direction. All right. On S2, the divergence div of a vector field x, if your vector field x is this, again, the determinant is this, the square root of the absolute value of the determinant of the metric sine theta, and gives you this. So div x is, and then you can just write out the components like this. So that one plus that one. Now, this is sine theta, so you can replace this with sine theta, this with sine theta to carry out the various operations if you want to. Otherwise, just leave it in this form here, expressing in terms of the the tangent vectors, tangent basis vectors. Okay, like that. All right. Sorry, this is 1 on sine theta, partial derivative of all this with respect. So this is a scalar. There's no basis vectors. My apologies there. I'm rushing. This is the partial derivative of sine theta times the theta component of x, okay, with respect to theta. So the partial over partial theta. So the whole thing's a scalar. There's no basis vectors in here. My apologies. Getting a bit jumpy as I'm concerned that the video is getting a bit long. It's over 35 minutes already. My apologies. Anyway, let's return to 3D with metric tensor. This here in 3D, spherical polar coordinates. The determinant of the metric is this object here. Okay, you can see the square root of that will be r squared, the absolute value, the square root of the absolute value of that will be r squared sine theta. Not that we need to take the absolute value there. The curl components are this, remember this, and just to give you the example here, if we wanted the r component, then we'll have this. We've got to put into the Levi-Civita symbol. Mu will be r, so mu, r, that'll be r as well. And then the only other components we've got are then theta and phi. So theta, phi, well, r theta phi, that's gives us +1, but an odd permutation would be r phi theta, where theta and phi have been interchanged. That will give us a negative because it's an odd permutation. And so r theta phi is plus, but r phi theta is negative, and then you have these partial derivatives here. Okay, so in conclusion, in differential geometry, grad, curl, and div are naturally defined using the exterior derivative, the Hodge-Star operator, and the metric tensor. The use of differential forms provides a coordinate-free way to generalize these operations to curved manifolds, ensuring compatibility with tensor calculus and general relativity. Since in general relativity, we don't want our results dependent on our coordinate system. They're not. They're independent of our coordinate system. Our coordinates are just labels for phenomena. And they're not physical phenomena in themselves, they're just labels. All right, so on a curved manifold, we have the following results. The gradient vector is df, sharp operator acting on df. It has components this, expanded in terms of the tangent basis vectors here. The divergence of a vector x is this object here. It should produce a scalar. Its components are this object here, which is just a scalar, no basis vectors here. And then the curl, which is a vector, which is this object here, has components this. All right, if you want the components only, it's this. All right, and that's what we've done. So that's what we found for this video. I hope that was useful to everyone. I hope I haven't rushed you. I know it's one of the longer videos, but I hope that's clear to everyone, and I hope you find it useful. If you do, please push the like button and subscribe. If you can, share the channel around if you will. I'd greatly appreciate it if you would. I wish everyone well, and I shall see you in the next video. So please take care and have a good day. Okay, bye.